Okay, so now what happens when we share electrons? So the number of covalent bonds that a nonmetal atom forms is usually equal to the number of electrons it needs to achieve that stable electron arrangement. Okay, so you have a couple of different pictures here you can look at. So we have a methane molecule, an ammonia molecule, water, or handy dandy H2O made into amazing lemonade, right? Okay. So given the formula of a molecular compound, write the correct name, and given the name of a molecular compound, write its formula. So those covalent bonds, again, are the strong guys, and they form when atoms of two or more nonmetals share the electrons and form that covalent bond. The valence electrons are shared by nonmetal atoms to achieve this stability. So the electrons just kind of buzz around and go between both of them, and they're just very nicely shared. And a molecule forms when two or more atoms are going to share those electrons. So basically, this is like how we are going to form a hydrogen molecule. So a hydrogen molecule is written as H2. And this forms as the atoms move closer, and the positive charge of the nucleus is going to attract the electron of the other atom, because remember, opposites attract. It has a shared pair of electrons that form that covalent bond, that shared bond, to give each atom that stability, that noble gas arrangement of He to each of the hydrogen atoms. And it's more stable than individual hydrogen atoms. Okay, so helium is more stable than the hydrogen. And so basically, like I said from the beginning of this chapter, all we're trying to do is get to the right electron count so that our orbitals are full. So if we have like only a few buzzing around on the outer orbital, we donate them. Or if we need a few more to make us full, then we're going to borrow them. And so it all just equalizes out. Okay, so let's move me out of the way. All right, so the formation of a hydrogen molecule, again, your energy level increases, the distance between the nuclei decreases, and this is when the covalent bond forms as the hydrogen atoms are going to move closer together to be able to share those electrons. So you can see these guys are far apart, there is no attractions, but then the attractions are going to pull them close together, and then when they bond and share that charge, then we have a stable molecule down here. Okay, so let's move that here. So this is electron-dot formulas, and this is how we keep track of those electrons, okay? And this is how we're going to draw those molecular compounds. So to draw the electron-dot formula of a fluorine molecule, F2, we're going to start with the electron-dot symbols for each fluorine atom. And so we have the fluorine atom here with 2, 4, 6, 7. Okay, 2, 4, 6, 7. Each of them are missing one, right, to make it full and happy. So then what happens is they're going to bond together and share that last guy, and it's going to be able to zip between, both of the different fluorines and just be happy. And then this is what is that covalent bond. And so now where we had kind of an unstable one with by itself, when they bond together and form that covalent bond and they kind of snuggle, then they can share that one and then they become very stable. And this is good for us because then things don't explode. Okay, so each fluorine atom is going to share one electron to form a covalent bond, therefore giving each fluorine that stability of that octet bonding. The diatomic molecules, okay, these are going to be the elements of hydrogen, nitrogen, oxygen, chlorine, bromine, and iodine, and these exist as diatomic molecules. And so here's where they are in the periodic table. And so you might want to, remember that these are going to be those diatomic molecules. So di means two, right? So H2, N2, O2, F2, Cl2, Br2, and I2. Those are going to be your diatomic molecules. And what we're going to do is share electrons to make everybody happy. So the number of electrons a non-metal atom shares and the number of covalent bonds it forms are usually equal my cat's funny, to the number of electrons it needs to achieve a noble gas arrangement, or that octet, that stability, right? So if we have, this is typical bonding patterns of some nonmetals. We have the hydrogen is 1 bonds, or 3 bonds, 4 bonds, 3 bonds, 2 bonds, 1 bond. Okay, so it tells you where the positions are and how many bonds they have. So what are we going to work on? Being able to draw those electron dot formulas. I have to show you guys this. You really don't care, but so cute. Hi, Sophie. She's like, you woke me up, Mom. I'm not very happy with you. Okay, so to draw the electron dot formula for methane, we're going to start by drawing the dot symbols of the two parts of it. So the carbon and the hydrogen. So the carbon has 4, right, where the hydrogen only has 1. And so the carbon needs 4 hydrogen atoms to complete the noble gas configuration for the carbon and hydrogen. And so that means that we're going to have the 1, 2, 3, 4, because we have 4 by itself, and then that orbital is going to be 8. So 4, 5, 6, 7, 8 to be a happy camper. And so we have the 4 individuals from the carbons, and then the 1 additional from the hydrogen. And so then that ends up being a straight 8, right? And like I said, a kind of a happy camper. The electron dot formulas for common molecules such as methane, ammonia, and water are going to be shown here. And again, just try to get to that magic 8 number by filling with hydrogens. So figure out what your center guy has, and then, like, I call it hydrogens are filler molecules, right? So they make it so things are stable. If we need them, we pull them in. They're great sharers, and that's awesome. Okay, so again, looking at our CH4, NH3, H2O, draw the carbon. It has 4 by itself, and then it needs 4 to be stable, right? Then our nitrogen and our oxygen. So you can, just work these together and figure out basically stability, because we don't want things to explode, and to not explode, we want that orbital full. As always, there are exceptions, and so while the octet rule is useful, there always are exceptions. Hydrogen just requires 2 electrons to form a noble gas arrangements, where nonmetals P, S, Cl, Br, and I can form compounds with 10 or 12 valence electrons. And the S atom has an octet and many compounds, but in SF6 there are 12 valence electrons, or 6 bonds to the sulfur atoms. So again, just random little sides to note. We can also have double and triple bonds, and so a double bond occurs when atoms share 2 pairs of electrons instead of just 1. So it would be like C double bond C, right? That would be a double bond, right? And this forms when there are not enough electrons to complete those octets, so then they bind with each other a little bit stronger, so they don't have to fill those placeholders with hydrogens. And same thing with the triple bond. This occurs when atoms share 3 pairs of electrons, and it forms when there is not enough electrons to complete those octets. So our handy dandy guide to drawing electron dot formulas. So 1, let's determine the arrangement of the atoms. 2, let's determine the total number of valence electrons. 3, let's attach each bonded atom to the central atom of the pair of the electrons. And then 4, let's place the remaining electrons to complete the octets. 2, 4 hydrogens. All right, so step 1, okay, so here we're going to draw the electron dot formula in the carbon dioxide, CO2, in which the central atom is carbon. So determine the arrangement. We have central atom carbon, oxygen on either side, CO2. And then let's determine the number of valence electrons. So our carbon has 4 electrons, right? And then our oxygen has 6 electrons. We have 2 of them, so that ends up giving us 12 electrons, because 6 times 2 is 12. You add 4 plus 12, and that ends up giving us 16 valence electrons for the CO2 formula. So let's draw this. So we're going to attach each bonded atom to the central atom with a pair of electrons. So we have that carbon bonded to the oxygens. And then we have to replace the remaining electrons using single or multiple bonds to complete the octets. Okay, so the lone pairs are converted into binding pairs. Okay, so you can either write this like this guy, you know, or we're going to do lines for bonds too. And so this, when they're stacked like that, is going to be the double bond. Personally, I like the equal sign for a double bond, but that's just me. And so this is basically what we're going to end up doing. And the reason we made that double bond is because that carbon needed to have more guys filled. Okay, and we didn't have enough. So that is how we are going to do that. Right. So moving on to form triple bonds. An example of this would be with nitrogen. So nitrogen, each nitrogen atom shares 3 electrons to be able to gain that octet status. And the multiple bond formed is called a triple bond. And this is the name, the name is the same as that of the element. And so again, you can do the dots. The 3 on top of each other would be the triple bond, and then that's what it would look like. So when naming covalent compounds, the first nonmetal in the formula is named by the elemental name. The second nonmetal is named by using the first syllable of its name followed by ide. And then if a subscript is used in the formula, then the prefix is used in front of its name. When the vowels O and O or A and O appear together, the first vowel is omitted. All these rules, I tell you. But it's kind of cool how it all works out and makes it all work together. So prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, octamon, nona, or deca. So this one might be a good one again to remember. Okay. So here is some common molecular compounds. CS2 is carbon disulfide. Okay, carbon dioxide, nitrogen oxide, dinitrogen oxide, sulfur dioxide, sulfur trioxide, and sulfur hexafluoride. And so again, just break it down to those root words, and those will really help. Okay. So your handy dandy little guide to naming molecular compounds. So name the first nonmetal by its elemental name, and then name the second nonmetal by using the first syllable of its element followed by ide, and then add prefixes to indicate the number of atoms. And that's the number in the subscripts. So let's name the covalent compound NCl3. So N would be nitrogen, and then we're having chloride, but there's 3 of them with that superscript, so then that would give us that prefix or the word tri. So then this guy would be the first nonmetal is nitrogen, and the second nonmetal is chloride. So remember, we're putting that suffix of ide, and because there's 1 nitrogen atom, no prefix is needed, and the subscript 3 is for the chlorine atoms, and then this is going to be tri. So then this NCl3 would be nitrogen trichloride. 1 nitrogen, 3 chlorides. Okay? All right, so let's do a little study check here. So select the correct name for each of these compounds. Pause. Come back. All right, so this is silicon tetrachloride, diphosphorus pentaoxide, dichloride heptaoxide. Sometimes I wonder if I'm even speaking English, you guys, but you guys get it, so we're good. All right, again, write the name of each of the covalent compounds. Pause me, come back. All right, so this guy, first nonmetal is carbon, first nonmetal is nitrogen, first nonmetal is phosphorus, first nonmetal is carbon. Second nonmetal is oxide, second nonmetal is oxide, second nonmetal is fluoride, second nonmetal is chloride. So putting these two together for our solutions, then this is going to be adding the prefixes to indicate the number of atoms. So A, C, O. Since there's only one carbon atom, no prefix is needed, and the subscript 1 for oxygen is shown by mono. So CO would be carbon monoxide, carbon monoxide, the bad guy, right? It makes us very sleepy and kills us. NO2, because there's one nitrogen atom, no prefix is needed, and the subscript 2 is for the oxygen atoms shown, and so we're going to use di, so then that would be nitrogen dioxide. Okay, then PF, I'm going to say PF jinx, PF3, because there's one phosphorus atom, no prefix is needed, and the subscript 3 for F is shown as tri, so it would be phosphorus trifluoride. Okay, same thing with this. This would be carbon tetrachloride. Okay, so practicing this a little bit more. So how do we do this to write the formula names of the molecular compounds? One is going to be writing the symbols in the order of the elements in the name, then writing any prefixes or suffixes. Okay, so write the formula for the covalent compound diboron trioxide. So the first nonmetal is boron, the second one is oxygen. So then let's write down the prefixes. The prefix di in diboron indicates 2. The tri in trioxide indicates 3. So then our solution would be B2O3. So let's practice this a little bit more and write the correct formula for each of the following. Pause me and come back. Okay. So let's write the symbols in order of the names of the elements. Phosphorus pentachloride. First nonmetal is phosphorus, second is chloride, so PCl. Dinitrogen trioxide. First nonmetal is nitrogen, second one is oxygen. Sulfur hexafluoride, sulfur, and then fluoride. Step 2, let's follow those words and write any prefixes and subscripts. So phosphorus pentachloride, there's no prefix for phosphorus, so that indicates that there's only one. But penta in pentachloride indicates that there are 5 after the chloride, so that would be PCl5. Dinitrogen trioxide. Di and dinitrogen gives us 2. Okay, the tri and trioxides gives us 3. So then that would be N2O3. All right, so write any prefixes. Okay, so for C, again, there's no prefix for sulfur, and that indicates that there's only one. And the prefix of hexa and hexafluoride indicates that there are 6 fluoride atoms. And so then we would have SF6. All right. So here is our naming flow chart. All right, and so we have, if it's ionic, nonmetal, or metal, or molecular with 2 nonmetals, metal or ammonium, nonmetal, okay, mono, polyatomic, so you guys can read through this. And again, that'll just be a really good referral table for you. All right, last question for this one. So identify each compound as ionic or covalent and give its correct name. So pause and come back. All right, so SO3 is sulfur trioxide, and this is a covalent bond. Barium chloride is the ionic. Okay, ammonium phosphate is ionic. Copper carbonate is ionic, where the dinitrogen tetraoxide is the covalent. Okay, so great job, guys.